Welcome back, everyone. If you're in 8th class, you are in exactly the right place. Okay, let's dive right into this explainer and crack one of the absolute coolest math mysteries out there. Yep, we're heading back to the scene of the famous locker puzzle, and today we're finally solving the case. Here's our learning roadmap for today. We'll quickly look at the locker puzzle returning, figure out exactly what a factor is, learn the rule of pairs, uncover the square number secret, finally solve the locker mystery, and then wrap up with some quick revision and practice. Section 1, the locker puzzle returns, refreshing the rules of the game. Let's remember exactly where we left off last time. Remember our massive clue from our last session? A locker gets toggled exactly as many times as its number has factors. So step 1, if the number of factors is even, the locker ends up closed. And step 2, if the number of factors is odd, it stays open. Keep those two rules locked in your brain. They're our primary clues. But here's the big question. When we looked at the final open lockers, they were all square numbers. But why? Why do only square numbers have an odd number of factors? Why does every other normal number have an even amount? That's what we're going to figure out today. Moving right along to Section 2. What is a factor? Unlocking the basics. To crack this case, we have to know our building blocks. So the crucial point is this simple definition. A factor is just a number that divides another number exactly, without leaving any remainder behind. It's perfectly clean division. Let's test it out with the number 12. Which numbers divide perfectly into 12? Well, 12 divided by 1 is 12, so that works perfectly. 12 divided by 2 is 6. Divided by 3 is 4. Divided by 4 is 3. Divided by 6 is 2. And 12 divided by 12 is 1. So our resulting factors for 12 are 1, 2, 3, 4, 6, and 12. Count those up, and 12 has exactly 6 factors. 6 is an even number, right? Remember, finding factors is literally just about exact, clean division. Nothing more, nothing less. All right, Section 3, the rule of pairs. Partners in math. Time to spot a pattern. Look carefully at how these factors grouped together. 1 times 12 is 12, 2 times 6 is 12, 3 times 4 is 12. Notice anything? Every single factor has a partner. We've got 3 pairs, which gives us exactly 6 total factors. Let's try it with 20. 1 times 20, 2 times 10, 4 times 5. It's the exact same story. Every factor has a partner A and partner B. 3 pairs again, meaning exactly 6 total factors. This brings us to a huge revelation. We call it the rule of pairs. Because factors normally come in pairs, the total number of factors is always going to be an even number. They never write alone. Normal numbers will always have an even number of factors. Section 4, the square number secret, the twist in the tail. Okay, if normal numbers always have an even number of factors, how on earth can any locker stay open? Well, look at the number 9. Think about how we multiply numbers to get 9. Does anything seem a bit different compared to 12 or 20? Let's check its factor pairs. 1 times 9 equals 9, totally normal. But then 3 times 3 equals 9. Bam, there's our aha moment. For 3 times 3, both numbers are exactly the same. The number 3 pairs with itself. It doesn't have a different partner. So when we list the distinct factors, it's just 1, 9, and a single 3. That's 3 factors in total. And 3 is an odd number. Let's test this anomaly out with a couple more examples. Check out the number 4 on the left. The factors are 1 times 4 and 2 times 2. 2 pairs with itself, so our list is just 1, 2, and 4. 3 factors. Odd. Now look at 16 on the right. 1 times 16, 2 times 8, and 4 times 4. 4 pairs with itself. So the list is 1, 2, 4, 8, and 16. That's 5 factors. Another odd number. And this brilliantly illustrates our secret pattern. 1 is 1 times 1. 4 is 2 times 2. 9 is 3 times 3. These are perfect square numbers. In every single square number, one factor is repeated. It pairs with itself, leaving one factor without a separate partner. And that is exactly why square numbers, and literally only square numbers, have an odd total number of factors. Section 5. Solving the locker mystery. Case closed. Time to take all these clues back to the hallway. Let's put locker 12 and locker 16 side by side. 12 is a normal number. It has 6 factors. 6 is even. So, toggled an even number of times, locker 12 ends up totally closed. But 16, it's a square number. It has 5 factors. 5 is odd. Because it was toggled an odd number of times, locker 16 stays wide open. So, out of all 100 lockers in the school, the only ones that stay open at the very end of the game are the perfectly square ones. Lockers 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. We officially solved it, detectives. Case closed.
Finally, Section 6, quick revision and practice. Exam prep time. Let's make sure you're 100% ready to ace your exams.
Let's quickly retrace our steps. There are 4 main points you need to remember. 1, factors usually come in pairs. 2, square numbers break this rule because they have one repeated factor, like 4 times 4. 3, because of that, square numbers will always have an odd total number of factors. And 4, because of that odd number, only square number lockers stay open at the end of the puzzle. All right, quick practice time for you all. What are the factors of 36? How many factors does 49 have? Is 64 a square number, and why? Why does 16 have an odd number of factors? And which lockers remain open? I highly encourage you all to pause the explainer right now, grab a notebook, and test yourselves on these questions. You guys did absolutely amazing today. We learned what a factor is, we cracked the rule of pairs, and we uncovered the odd factor secret of square numbers to solve the entire locker puzzle. But our math journey doesn't stop here. Now that you know what makes these numbers so special, how do you think we write them using that cool square notation in our textbooks? What's the deal with that little tiny 2 floating up in the air? I'm going to leave you with that provocative thought, and I can't wait to show you exactly how it works with some easy diagrams in part 3. Keep exploring, and I'll see you next time.